Lecture 20 covers sections 6.5 through 6.7. At the end of today's lecture, you should be able to derive the thermodynamic property relations, i.e. Gibbs equations. You should also be able to apply Gibbs equations to incompressible substances such as solids and liquids. You should also be able to apply Gibbs equations to ideal gases, and you should be able to define standard entropy for ideal gases. To begin, we are going to state our goal for this lecture, and our goal is to relate entropy, S, to other state properties, such as our internal energy, our pressure, our enthalpy, etc. And to do such, we're going to look at the conservation of energy equation, i.e. the first law of thermodynamics, which states our heat supplied is equal to the change of internal energy plus the work done by our system. If we consider a compressible substance undergoing a reversible process, our heat added, delta Q, is equal to our temperature times our change of entropy, TdS. The work done during this process would be PdV. Substituting these two expressions back into our conservation of energy equation, we can say delta Q is equal to du plus delta W would be equal to TdS is equal to du plus PdV. We see we can calculate the change of entropy, ds, within our system if we know our temperature, our change of internal energy, our pressure, and our change of volume. Now this formulation is valid for both reversible and irreversible processes, because we note that we have ds, du, and dv, which are state variables. That is, it does not depend upon the path of how we go from our initial to our final state. Likewise, if we re-examine the first law equation, and we recall our definition of enthalpy, which is equal to internal energy plus our pressure times our volume, we can express our change of enthalpy as du plus pdv plus vdp. Now if we substitute this expression into our conservation energy equation, where du is equal to dh minus pdv minus vdp, we'd have our heat supplied would be equal to dh minus pdv minus vdp plus our work, which is pdv. And we notice our pdv terms cancel out. Thus our second Gibbs equation is TdS is equal to dH minus VdP. These two equations are known as our thermodynamic property relations, or our Gibbs equations, and they can be evaluated on a per mass basis and for a variety of processes. Now let us look at how we could apply these equations. Say we want to determine the change of our specific entropy of R134A, which goes from a saturated liquid to a saturated vapor at a temperature of 0 degrees centigrade. To do such, we would recognize that this phase change process occurs under constant pressure. Therefore, if we look at our Gibbs equations, we'd recognize the second would be most useful, for dP would drop out. Thus, if we look at the second formulation of Gibbs equations, TdS is equal to dH minus vdP, we'd have T ds is equal to dH, which is expressed on a per mass basis. Or we can say our change of entropy, ds, would be equal to our change of enthalpy, dH, per temperature, which is equal to h sub g minus h sub f per T. If we use table B.5.1 on page 811 of our steam tables, we'd have HFG being equal to 198.36 kJ per kg, and this is occurring at our saturation temperature of 273.15 Kelvin. Thus our change of entropy is 0.726 kJ per kgK.